In this video, I'm going to cover electron configuration and how to fill orbitals. First of all, starting with the idea that we've got electrons in an atom that exist in energy levels. Each energy level is given a number, an integer, denoted n, so 1, 2, 3, 4, 5, etc. And one thing we'll work with is this rule. The nth energy level has n sublevels and can hold 2n squared electrons. Before we delve a bit deeper, what is a sublevel? There are 4 different types of sublevels that we deal with in chemistry. They've all got different shapes. So we've got the s orbital, which is round, the p orbitals, which are dumbbell shaped, the d orbitals, which have more complicated shapes with usually 4 lobes, and then the f orbitals, which are really complicated. In each of those sublevels, you've got 1 s orbital, which is just round in shape, 3 p orbitals because they point in different directions. You've got one along the x-axis, one along the y-axis, and one along the z-axis. You've got 5 d orbitals and 7 f orbitals. Okay, so each individual orbital can hold 2 electrons, so the s orbital in total can have 2 electrons. The p orbitals, because there's 3 of them with 2 each, they can hold 6 electrons. The d orbitals can hold 10 and the f orbitals can hold 14 because there's 7 of them. And that's nicely covered by our rule. The nth energy level has n sublevels and can hold 2n squared electrons. If we look at that using the table in your booklet that you have to fill out, we've got energy level 1, for example. You can have 2n squared electrons in that energy level. So n is 1, 1 squared is 1, times 2 is 2. So there's 2 electrons allowed in that level. It has 1 sublevel, because it's the first energy level, and that's s. Okay, so it holds 2 electrons. If you look at an energy level 2, then you've actually got a total of 8 electrons that are allowed, because 2 squared is 4 times 2 is 8. And they're organised into 2 different sublevels, because it's energy level 2. The s, there's 1 s orbital, and it can hold 2 electrons. And there's 3 p orbitals, and they can hold 6 electrons. And it keeps going as you go down. You've got energy level 3. 3 squared is 9. 9 times 2 is 18, so you can put 18 electrons in that level. And they're divided into 3 sublevels because it's n equals 3. The s, p, and d, which can hold 2, 6, and 10 electrons. Okay, so that begs the question, how are those orbitals filled? If we're making an atom, what electrons do we put in what orbitals and in what order? The rule that governs this is the Aufbau principle, which says that electrons are placed in orbitals of lowest energy first. So, which one's the lowest energy? I recommend drawing this orbital filling diagram, which you find over here on the left side of the screen. I'm going to show you how to do one. You can use the periodic table to help. I've tried to color code everything so that you've got your s orbitals or your s block of your periodic table, which is red or pink-ish. You've got your p block of the periodic table, which is yellow, like your p orbitals over here. You've got your d block, where the d electrons are filled, which is blue in the middle there, and the f block we don't really deal with, but they are in green. So, if you're going to draw that diagram for yourself, what I recommend is putting the energy levels up the left-hand side, like that, 1, 2, 3, 4, 5. You can keep going, there's no reason you can't go to 6 or 7, but it doesn't come up very often, because we usually only deal with the elements in the middle of the periodic table there. Color code. The first electrons to fill are the first 2 elements in the periodic table. They correspond to those. So the first electron would go in hydrogen and the second electron would go in helium. Though that's the 1s orbital, and you can put 2 electrons in it. So 1s2, 2s2, 2p6. Now the next 6 elements are in the p block. So the next 6 electrons all go into p elements. The next one to be filled, going from neon over to sodium, which is number 11, are the 3s orbitals, 2 in there. And then the 3p orbitals, there's 6 in there, so that's given the label 3p6. Then you come down and you fill the 4s orbitals. In the orbital filling diagram, it might look as if you should do the D next, because that's the next logical choice. But that actually comes after the 4s, because potassium and calcium come before the D elements in the periodic table. So then you do the 3d orbitals. There's 10 electrons that can be put in those orbitals. Then the 4p6, then the 5s2, the 4d10, the 5p6, and then you do the 6s2 and so on and so forth. But I've just put the rest of the diagram in so you can sort of see that. Some examples would probably be the nicest way to show you how it's done. So let's say I need, oh hang on, I've got my arrows in, to show the filling order. So when you do your orbital filling diagram, which I forgot to finish off essentially, you've got your 1s orbital there, and that's filled first. And to do the order, you just need to draw diagonal lines up through the orbitals so that you know what order they're filled in. So you fill them in the order of 1s2, then 2s2, 2p6, 3s2 following the diagonal line, 3p6, 4s2 again following the diagonal line, then 3d10, 4p6, 5s2, 4d10, 5p6, excuse me, and 6s2 would be next if I'd put it in. So let's have a look at sodium. That's a nice easy example. Sodium has 11 electrons, so we need to put 11 electrons in there. We start at the beginning. As the Aufbau principle says, we place electrons in orbitals of lowest energy first. So we put in the 1s2 electrons, 2 of them. We put in the 2s2, 2 of them. The 2p6, 6 of them. And we've actually only got 1 electron left, and you can see it's one of the 3s electrons. It's just a matter really of looking at where sodium is in the periodic table and saying, okay, well, I've filled all of the orbitals before there, the 1s2, the 2s2, the 2p6, and here I'm in row 3, and I'm in the first group, so that's 1 3s orbital. And if you count up the little superscripts here, 1s2, 2s2, 2p6, 3s1, 2 plus 2 plus 6 plus 1 is 11. Sodium's got 11 electrons. That is the ground state electron configuration of sodium. If you like, as a shortcut, you can actually use this symbol which says the electron configuration of neon. So it's like saying, okay, it's the same as neon, and then an extra S electron, which is in the 3rd energy level. Okay, so because neon has the electron configuration 1s2, 2s2, 2p6, but instead of writing that, we can just write neon in those square brackets. Here's another one, arsenic. It's got 33 electrons because its atomic number is 33. So we just start filling until we get to 33 electrons, or until we get to that location in the periodic table, whichever way you'd like to do it. So 1s2, 2s2, 2p6 following the diagonal lines up here, and we know 3s2 is next. That's over here in the periodic table. 3p6, 4s2, the whole D block is filled in that area there, 3d10, and then arsenic is the 3rd p block element over. Okay, so it's the 4p elements, and it's the 3rd one over, so we say 4p3, and that's the electron configuration of arsenic. Again, you can shorten it if you like. You can say, okay, well, the noble gas immediately before that is argon, right? So it's, we haven't got krypton yet. That's 3 in advance. The one before that is argon, so we can say, okay, everything in the electron configuration of argon, so we put those square brackets around it, and then say, okay, in addition to that, we've got the 4s2 elements, the 3d10, and 3 of the p elements. I just put a transition metal in as well, just for one extra, because they're very, very common in IB questions. They really like asking you electron configurations of the transition elements. So 26 electrons for iron, 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, and it is in the D block. You've got scandium, titanium, vanadium, chromium, manganese, and iron. It's the sixth one across, so it's going to be 3d6. You can check that if you like by adding up the numbers in the superscripts. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So if you add them up, 2 and 2 is 6 is 10, 2 and 6 and 2 is 10, plus 6 is 26. So that's the 26 electrons that are in iron. Again, you can shorten it. Argon's the previous noble gas, so put your electron configuration of argon plus the 4s2 electrons and the 6d electrons in the 3d level. And that's basically it. Next we'll start off on taking electrons out. So if I turn that iron atom into an iron-iron, then I'm losing 2 electrons because it's Fe2+. So instead of having 26 electrons, I've got 24 electrons. The trick here, which I'll discuss maybe in another video or in a tutorial online sometime, is that you keep everything else the same, but the 2 electrons that come out are actually the 4s electrons. We put them in first, but the odd thing about the transition metals is that we take them out first as well. In a way, this is a bit of a lie. What I've taught you today, this orbital filling diagram, it's really a trick, a model for finding out what the electron configurations of all of the elements are. And it's true for a lot of the elements. For the transition metals, it's not really. The 4s electrons aren't actually lower energy than the 3d, they're higher, but it's a really complicated situation. So we still use this orbital filling diagram to work out what the electron configuration is, but we have to use the amended rule that when you're removing electrons, the 4s electrons are actually higher in energy, so we take them out first. So what we're left with is we've got 24 electrons, but instead of being 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, which you might expect, it's actually 1s2, 2s2, 2p6, 3s2, 3p6. The 4s electrons are gone, you take them out first, and the 3d6 electrons remain. And you can just put that electron configuration together like you always would, and shorten it if you like to argon 3d6. Alright, that's it.